February marks the 21st anniversary of the tragic events of the Space Shuttle Columbia. Before we get into this, my name is Phil, and this is the Fun-Filled Fact Factory. We're going to go into a deep dive of the Space Shuttle Columbia and its tragic events. But before we do that, I need everybody to either shake your pom-poms or like and subscribe. It's your choice. The Space Shuttle Columbia was designed as a partially reusable spacecraft operated by NASA. Its first flight into space was April of 1981. It consisted of the orbiter, which contained the crew and payload, the external tank, and the two solid rocket boosters. The orbiter, or shuttle, was a reusable vehicle that launched vertically and landed as a glider. The shuttle was coated with a protective layer around it to withstand the extremely high temperatures during re-entry. The reusability of the shuttle required a multi-use heat shield. During re-entry, the protective layer experienced temperatures of up to 3,000 degrees, but had to keep the orbiter's vehicle aluminum skin temperature below 350. The skin primarily consisted of four subsystems. The nose cone and the leading edges of the wings experienced temperatures of above 2,300 degrees and were protected by reinforced carbon-carbon material, RCC. The entire underside of the shuttle, as well as the other hot surfaces, were protected with a black, high-temperature, reusable surface insulation. Areas of the upper parts of the orbiter vehicle, or shuttle, were covered with a white, low-temperature reusable surface insulation, which provided protections of temperatures below 1,200 degrees. The payload doors and parts of the upper wing surfaces were covered with a different insulation that really only covered up to 700 degrees. During the design process of the space shuttle, a requirement of the external tanks was that it would not release any debris that could potentially damage the shuttle and its thermal protection system. The integrity of the thermal protection system components was absolutely necessary for the survival of the crew during re-entry. The tiles and panels were only built to withstand relatively minor impacts. The bipod connection between the shuttle and the external tank was covered in foam to prevent ice from forming that could cause damage to the shuttle. The foam on each bipod ramp was approximately 3 foot by 1 foot by 1 foot and was carved by hand. After a bipod foam strike damaged the thermal protection system on STS-50, internal NASA investigators concluded that it was an acceptable flight risk and that it should not be treated as a flight safety issue. Bipod foam loss occurred on STS-52 and 62, but neither event was noticed until after the investigation following Columbia's destruction. On the first flight of the space shuttle, the shuttle Columbia was damaged during its launch from a foam strike. The foam strikes occurred regularly during space shuttle launches. Of 79 missions available imagery during launch, foam strikes occurred on 65 of them. For STS-107, the Space Shuttle Columbia carried the following experiments and equipment. The Space Hab Research Double Module for the purpose of private research, and once destroyed, the company filed a formal complaint against NASA for approximately $88 million, of which they only received $25 million between insurance and NASA. Second, the Orbiter Acceleration Research Experiment, which is to measure with high accuracy and low frequency the low magnitude acceleration levels on board the space shuttle. The shuttle experiences acceleration from atmospheric drag, gravity, gradient forces, shuttle rotation, crew activities, water and waste dumps, the shuttle's altitude thrusters. All of this data and information is utilized by microgravity scientists. And last, the Extended Duration Orbiter Pallet. This was used for the shuttle's endurance for prolonged missions by supplying additional hydrogen and oxygen for its fuel cells. The mission passed its pre-launch certifications and reviews and proceeded with the launch. The mission was originally scheduled to launch on January 11, 2001, but it was delayed 13 times until its launch on January 16, 2003. The 7-member crew of the STS-107 were selected in July of 2000. The mission was commanded by Rick Husband, who was a colonel in the U.S. Air Force and a test pilot. He had previously flown on STS-96. The mission's pilot was William McCool, a U.S. Navy commander who had his first spaceflight. The payload commander was Michael Anderson, a U.S. Air Force lieutenant colonel who had previously flown on STS-89. Kalpana Chawla served as the flight engineer. She had previously flown on STS-87. David Brown and Laurel Clark, both Navy captains, flew as the mission specialists on their first space flights. Elian Ramon, a colonel in the Israeli Air Force and the first Israeli astronaut, flew as the payload specialist. Columbia launched from the Kennedy Space Center Launch Complex 39A at 10:39 a.m. At T plus 81.7 seconds, a piece of foam approximately 21 to 27 inches long and 12 to 18 inches wide broke off of the left bipod on the external tank. At T plus 81.9 seconds, that foam struck the reinforced carbon-carbon panel on Columbia's left wing at a relative velocity of up to 573 miles an hour. The foam's low ballistic coefficient caused it to lose speed immediately after separating from the external tank, and the shuttle ran into the slower moving foam. The mission or ground crew did not notice the debris strike at that moment. After Columbia entered orbit, the NASA Intercenter Photo Working Group conducted a routine review of the videos of the launch. The group's analysis did not notice the debris strike until the second day of the mission. None of the cameras that recorded the launch had a clear view of the debris striking the wing, leaving the group unable to determine the level of damage sustained by the shuttle. The group's chair contacted Wayne Hale, the shuttle's program manager for launch integration, to request an on-orbit picture of the Columbia's wing to assess the damage. After receiving notification of the debris strike, engineers at NASA, United Space Alliance, and Boeing created the Debris Assessment Team and began working to determine the damage to the shuttle. Intercenter Photo Working Group believed that the shuttle's RCC tile was possibly damaged. NASA's program managers were less concerned over the damage caused by the debris strike. Boeing analysts attempted to model the damage caused to the shuttle's TPS from the foam strike. The software model predicted damage that was deeper than the thickness of the TPS tiles, indicated that the orbiter's aluminum skin would be unprotected in that area. The debris assessment team dismissed this conclusion as inaccurate due to the previous instances of predictions of damage greater than actual damage. Further modeling specific to the RCC panel used software calibrated to predict damage caused by falling ice. The software predicted only 1 in 15 scenarios that the ice would cause damage, leading to the debris assessment team to conclude that there was minimal damage due to the lower density foam to ice. To assess the possible damage to Columbia's wing, members of the debris assessment team made multiple requests to get imagery of the orbiter from the DoD, or Department of Defense. Imagery requests were then channeled through both the DoD and Johnson Space Center. Engineering Director Hale coordinated the request through the DoD representative. That request was then relayed to the U.S. Strategic Command, which began identifying imagery assets that could be used to observe the shuttle. The imagery request was soon rescinded by NASA Mission Management Team Chair Linda Ham. After she investigated the origins of it, she had concluded with the flight director, Phil Indoff, and members of the mission management team who had stated that they did not have the requirements for the imagery of the Columbia. Ham did not consult with the debris assessment team and canceled the imagery requests on the basis that it had not been made through the official channels. Maneuvering the shuttle to allow its left wing to be imaged would have interrupted ongoing science operations, and Ham dismissed the DoD imaging capabilities as insufficient to assess the damage of the orbiter. Ham, scheduled to work as an integration manager on STS-114, was concerned about the potential delays from a foam loss event. Following the rejection of the imagery request, the debris assessment team did not make further requests for the orbiter to be imaged. Throughout the flight, members of the mission management team were less concerned than the debris assessment team about the potential risks of the debris strike. The loss of bipod foam on STS-107 was compared to previous foam strike events, none of which had caused loss of an orbiter or crew. Mission management also downplayed the risks of the debris strike in the communications with the crew. On January 23rd, Flight Director Stephen Stitch sent an email to Husband and McCool to tell them about the foam strike and inform them that there was no cause for concern about the damage to the TPS, as foam strikes had occurred on previous flights. On January 26th, the debris assessment team concluded there was no safety concern from the debris strike. The team report was critical for mission management for asserting that there was no safety concern before the debris assessment team's investigation had been completed. On January 29th, William Reddy, the Associate Administrator for Spaceflight, agreed to DoD imaging of the shuttle, but on the condition that it would not interfere with flight operations. Ultimately, the orbiter was not imaged by DoD during the flight. At a mission management team on January 31st, the day before Columbia re-entered the atmosphere, the Launch Integration Office voiced Ham's intention to review onboard footage to view the missing foam, but concerns for crew safety were not discussed. Columbia was scheduled to re-enter the atmosphere and land on February 1st, 2003. At 3:30 a.m. Eastern Standard Time, the entry flight control team started its shift at the Mission Control Center. On board the shuttle, the crew stowed loose items and prepared their equipment for re-entry. At 45 minutes before the deorbit burn, Husband and McCool began working through the entry checklist. At 8:10 a.m., the capsule commander, Charlie Hubaugh, informed the crew that they were approved to conduct the deorbit burn. At 8:15 and 30 seconds, the crew successfully executed the deorbit burn, which lasted 2 minutes and 38 seconds. At 8:44 and 9 seconds, Columbia re-entered the atmosphere at an altitude of about 400,000 feet, or 120 kilometers. The damage to the TPS on the shuttle's left wing allowed hot air to enter and begin melting the aluminum structure. 4.5 minutes after entry interface, a sensor began recording greater than normal amounts of strain on the left wing. The sensor data was recording in internal storage and not transmitting to the crew or ground controllers. The orbiter began to turn or yaw to the left as a result of increasing drag on the left wing, but this was not noticed by crew or mission control because of the corrections from the orbiter's flight control system. This was followed by sensors in the left wheel well reporting a rise in temperature. At 8:53 and 46 seconds, Columbia crossed the California coast. It was traveling at Mach 23 at an altitude of over 231,000 feet and had temperatures of the wing's leading edges was an estimated 2,800 degrees. Soon after it entered California's airspace, the shuttle shed several pieces of debris, events observed on the ground as sudden increases in brightness. The MMACS officer reported the hydraulic sensors in the left wing had readings below the sensor's minimum detection threshold at 8:54 and 24 seconds. Columbia continued its re-entry and traveled over Utah, Arizona, New Mexico, and Texas, where observers reported seeing signs of debris being shed. At 8:58 and 3 seconds, the orbiter's aileron trim changed from the predicted values because of the increased drag caused by the damage to the left wing. At 8:58 and 21 seconds, the orbiter shed a TPS tile that would later land in Littlefield, Texas. It would become the westernmost piece that was recovered in the debris field. The flight crew received an indication of a problem at 8:58 and 39 seconds when the backup flight software monitor began displaying fault messages for a loss of pressure in the tire of the left landing gear. The pilot and commander then received indicators that the status of the left landing gear was unknown, as different sensors reported that the gear was down or locked or in the stowed position. The drag on the left wing continued to yaw the orbiter to the left until it could no longer be corrected using aileron trim. The orbiter's reaction control system, or RCS, thrusters began firing continuously to correct its orientation. The loss of signal, or LOS, from the Columbia occurred at 8:59 and 32 seconds. Mission Control stopped receiving information from the orbiter at this time, and husband's last radio call of Roger was cut off mid-transmission.
Columbia, Houston, UHF comm check.
One of the channels in the flight control software was bypassed as a result of a failed wire, and a master alarm began sounding on the flight deck. Loss of control of the orbiter is estimated to have begun several seconds later with a loss of hydraulic pressure and an uncontrolled pitch-up maneuver. The orbiter began flying along a ballistic trajectory which was significantly steeper and had more drag than the previously gliding trajectory. The orbiter was still traveling faster than Mach 15 and entered into a flat spin of 30 to 40 degrees per second. The acceleration that the crew was experiencing increased from approximately 0.8 g to 3 g, which would have likely caused dizziness or disorientation, but not incapacitation. The autopilot was switched to a manual control and reset to an automatic mode at 9 o'clock and 3 seconds. This would have required the input of either husband or McCool, indicating that they were still conscious and able to perform functions at that time. All hydraulic pressure was lost, and McCool's final switch configuration indicated that he had tried to restore hydraulic systems at some time after 9 o'clock and 5 seconds. At 9 o'clock and 18 seconds, the orbiter began a catastrophic breakup, and all onboard data recording soon ceased. Ground observers noted a sudden increase in debris being shed, and all onboard systems lost power by 9 o'clock and 25 seconds. The orbiter's fore and aft sections had separated from one another. The sudden jerk caused the crew compartment to collide with the interior wall of the fuselage, resulting in a depressurization of the crew compartment by 9 o'clock and 35 seconds. During re-entry, all 7 of the STS-107 crew members were killed, but the exact time of their deaths could not be determined. The level of acceleration that they had experienced during the crew module breakup was not lethal. The first lethal event that the crew experienced was the depressurization of the crew module. The rate and the exact time of depressurization could not be determined, but occurred no later than 9 o'clock and 59 seconds. The remains of the crew members indicated that they had all experienced depressurization. The astronaut helmets have a visor that, when closed, can temporarily protect the crew member from depressurization. Some of the crew members had not closed their visors, and one was not wearing his helmet. This would have indicated that the depressurization occurred quickly before they could take preventative measures. During and after the breakup of the crew module, the crew, either unconscious or dead, experienced rotation on all 3 axes. The astronauts' shoulder harnesses were unable to prevent trauma to their upper bodies, as the inertia reel system failed to react significantly to secure them, leaving them only restrained by their lap belts. The helmets were not matched to the crew members' heads, allowing head injuries to occur inside the helmet. The neck ring of the helmet may have also acted as a fulcrum that could have caused spine and neck injuries. The physical trauma to the astronauts who could not brace to prevent such injuries also could have resulted in their deaths. The astronauts also likely suffered from significant thermal trauma. Hot gas entered and disintegrated the crew module, burning the crew members whose bodies were somewhat protected by the ACE suits. Once the crew module fell apart, the astronauts were violently exposed to wind blast and possibly shockwave, which stripped their suits from their body. The crew remains were exposed to hot gas and molten metal as they fell away from the orbiter. The pieces of the orbiter continued to break apart into smaller pieces, and within a minute after breakup were too small to be detected by ground-based video. By 9:35, all debris and crew remains were estimated to have impacted the ground. The loss of signal occurred at a time when the flight control team expected brief communication outages as the orbiter stopped communicating via the West Tracking and Data Reliability Satellite. Personnel in mission control were unaware of the in-flight breakup and continued to try and re-establish connection with the orbiter. A mission control member received a phone call concerning news coverage of the orbiter's breakup. This information was passed to the entry flight director, Leroy Kane, who initiated contingency procedures. At KSC, or Kennedy Space Center, where Columbia had been expected to land at 9:16, NASA Associate Administrator and former astronaut William Reddy also began contingency procedures after the orbiter did not land as scheduled. Look, not as fun as a daily video, but these deep dives are a way to look deep. So I hope that you stuck with it, you got your pom-poms, and then you liked and subscribed. Truly, I really appreciate you sticking around to the end. So Phil from Phil's Fun Fact Factory, thanks you again.